Welcome everybody to the Physics Department Colloquium. It's a pleasure for me to introduce to you our speaker, André Leclair from Cornell University. André has done an incredibly broad array of works, and part of the evidence of that is his schedule here while he was visiting involved meeting with condensed matter physicists, high energy physicists, and mathematicians. So that's a remarkable career in theoretical physics. André received his PhD at Harvard with Alvarez Gomez. There he met Mike Peskin, with whom he formed a close working collaboration for over the years. And after that, he did a postdoc at Princeton in the group of David Gross. And throughout this period, I think he tells me he was working very independently and finding his own path. And so that's a nice thing to aspire to for the students. That's what I mentioned. So a few months ago, Shucheng Zhang, our beloved former colleague, visited Cornell University and met André and was struck with André's insights into the title of the talk today on the Riemann Hypothesis and invited him over here to give the colloquium today. And I'm delighted to host André on Shucheng's behalf. Please.
All right, thank you. Well, thank you for showing up. Oh, I've got to turn this on here. Okay, maybe a little bit higher. Hello? Can you hear me? Okay, good. Yes, I didn't know this kind of talk is not typical of a physics colloquium, so I thank you all for coming. I never know what the turnout's going to be. Sri already explained why I'm here, which I wasn't sure he was going to mention, so I was prepared this slide here. I'm really sorry for your great loss, but Shu Cheng came to Cornell, gave these beautiful beta lectures, which are very prestigious set of lectures. He gave 3. The folklore at Cornell is that almost everybody who was given those lectures either had a Nobel Prize or got one soon after or later. And the list is quite incredible. So, I had worked a little bit on topological insulators, so I set up a meeting with Shu Cheng, but he wanted to hear more about the Riemann hypothesis. And I learned that he had some deep interest in this problem and knew quite a lot about it. So I was hoping to come maybe find a new collaborator by coming here. So unfortunately that didn't happen. But yes, he did have a deep interest in it, never wrote anything on it, but he knew quite a lot about the problem. And he could follow what I was saying pretty easily. So hopefully you will also. Okay, so we'll try to go through this. I have quite a lot of material here, so just based on some papers. I just want to show you that some of them are published. So 2 of them were published in some math journals, and a couple in some physics journals. So I'm going to start right off the bat and tell you what is this Riemann hypothesis. Not everybody knows what it is. Okay? So basically, the function was first studied for real values of z by Euler, but it's a very simple, very natural series to consider. And that series converges for the real part of z bigger than 1. Converges absolutely. Riemann analytically continued it to the whole complex plane. So he was quite an expert in complex analysis, and so he's the one that accomplished that. It has an infinite number of so-called trivial zeros. At every negative even integer, it has a 0. But those are kind of inherited from the properties of the gamma function. And it has a pole at z equals 1. Okay, so here's a quick picture. This is developed in terminology. It's hard to see my old slides here. So there's a so-called critical strip. So here are the trivial zeros. Okay. Then between 0 and 1, real part between 0 and 1 is called the critical strip. And x equals 1/2 is the critical line. And Riemann's hypothesis is that all the non-trivial zeros lie on this line. Okay? And here's a few of them. Okay? So they look like pretty random numbers. They're not so regular, but anyway, Riemann calculated a few of them. So his paper essentially opened up the whole field of analytic number theory. And it was a really short paper, something like 6 pages long, written over 150 years ago. And he wrote this, one would of course like to have a rigorous proof of this, that all the zeros are on the line, but have put aside the search for a proof after some fleeting vain attempts because it is not necessary for the immediate objective of my investigation. So I will tell you, I mean, he had a lot of results in that paper. They're still very, very important. So he did have an immediate objective that he did achieve, which I will tell you about. Okay. So this is a problem in analytic number theory. So the reason it's so important is that it has very deep implications for the distribution of prime numbers. That was his main result, actually, relating these zeros to the primes. And I'll explain to you how that comes about. In 1900, Hilbert proposed a list of 23 problems that should be solved, or should work on. Quite a few of them were, not all of them. This was one of them. So there's a famous quote. He said, if I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven? And we still don't know. Maybe in 1,000 years it still won't be proven. But there's a lot of evidence for it. So numerically, it's known that the first 10 to the 13th zeros are on the critical line. To mathematicians, that's not a huge amount of evidence. To physicists, we say, well, case closed, right? But it's known there's an infinite number of zeros, and 10 to the 13th is nowhere near infinite for mathematicians. There's not a really well-proposed strategy for this problem. So I'm going to propose a strategy. I'm not going to give you a proof, okay, but at least a strategy that's easy to, I think, for people here to grasp. It's a little bit physics-based. Well, there's money involved, which I know I will never collect, $1 million, but anyway, maybe somebody here will have some more ideas. I like this quote. So Selberg was a famous number theorist at the Institute for Advanced Study, and he said there had been very few attempts at proving the Riemann hypothesis because simply no one has ever had any really good idea for how to go about it. So there's not a lot of proposals out there. There's some. So I'm just going to give you a quick summary of some of what are the important ingredients of our particular approach. So the main idea is simple to explain, is that the primes are multiplicatively independent. Right? So if you know the millionth prime, you can't easily predict the next one. And there's a lot of primes. The list of primes is very long, especially toward the end. So we took this point of view of course, a large number is Avogadro's number, right? And we have the belief that maybe the Riemann hypothesis doesn't follow from the detailed properties of the primes, but some global properties. We can make some very strong predictions about a gas of particles without knowing the specific position, momentum of every particle, right? We're used to thinking that way. And that's the kind of point of view we'll be taking. So it's partly inspired by statistical physics. One nice thing about this approach is that there's at least two infinite classes of functions that are believed to satisfy the Riemann hypothesis. So, somebody might come up with something that works for one example, but then what about all the other ones? And some of them have very, very different definitions. So I'll be working on one type called Dirichlet L functions, but there's also L functions based on modular forms, and they're pure in string theory, and they're believed to satisfy a Riemann hypothesis too. And our methods apply to those cases, although I won't talk about it here, there's no time. So the analogy here is with Brownian motion and random walks. I'll tell you why. It's kind of a constructive approach. I mean, whether the Riemann hypothesis is true or not is sort of a yes or no question, but thinking of it in the way I'm going to describe is constructive, at least in new formulas. And just as an illustration, they'll tell you how I calculated the googolth zero. This is more, the 10 to the 100 is more atoms than there are in the universe. Mathematicians have gone up to about 10 to the 30. Some zeros are known around the 10 to the 30th to do somebody called Lisco. But here, I'll show you how I calculated this in a few minutes with Mathematica. Okay, quick outline. Like I said, I apologize, there's not going to be a whole lot of physics here, but I will start with a few places in physics where the zeta function appears. So maybe it'll just remind you that you actually know something about this function that you learned as an undergraduate, mainly in statistical physics. There's some other physics-based approaches. Most notably is this idea of Hilbert and Polya, that maybe there exists a Hamiltonian whose eigenvalues are the Riemann zeros. This idea has been around for a long time, and it's been pushed quite a lot, but so far it hasn't been very successful. So a lot of good things came out of it, but it still has a ways to go. So I won't talk about that. It would take too much time. I'm going to have to extend my definition. I want to look at this infinite class of functions called Dirichlet functions. And well, we're going to prove a few things. So the main result is that there's going to be a random walk for a certain series over the primes. And we're going to prove a central limit theorem for it. And a theme here is going to be a certain an interplay between randomness, random walks are random, but the primes are deterministic. Okay? So there's an interesting interplay there. In the last part of the talk, in a way, these two things are disconnected, but they kind of work together. So you can use this random walk property there's a different way to derive these transcendental equations I'll tell you about. And that's the application of putting these two ideas together is what led to these calculations of very high zeros. All right, how am I doing on time? Okay, so one place where the Riemann zeta function appears is in the Casimir effect. Okay, so I want to go through this quickly since I won't be using it all that much, but it's a way of motivating a very important relation that the zeta function satisfies. So let me first get into massless particles, photons, and let's look at them on a cylinder, but with one spatial dimension compactified with a circumference beta. So if I want to look at the 0-point energy, Casimir energy, it's a pretty simple calculation. These modes are quantized, the ones that are on the circle. Others are continuous. You integrate over those. You can do this integral, and there's a sum there. What's going to appear is this combination. Well, zeta of -3 is going to show up when you do this calculation. And gamma here is just the gamma function, which comes from these integrals, the two-dimensional integrals here. Now, what is zeta of -3? If you use the original definition that I gave you on the first few slides, well, it's obviously a divergent quantity. 1, 2 cubed, it diverges. But let me look at the problem in a different way. Let me exchange one of the space coordinates with time. So I'm going to go to Euclidean time, and this is going to be time here. Okay. Now it's well known that if you're doing quantum field theory on something of this shape, you're really doing finite temperature field theory. Okay, so beta here is now 1 over the temperature. And if you do this calculation, as you all from your undergraduate stat mech, it's just, now you have a 3-dimensional integral. This is the free energy. Basically, this is the free energy. There's BoseEinstein distribution. This integral is totally convergent, and you get something that involves zeta of 4. Okay, so actually, I looked at Planck needed this. Well, there's the pi squared over 90 you recognize in the black body formula. If you look at Planck's paper, which was the birth of quantum mechanics, he had to calculate zeta of 4, but didn't know, I don't think he knew it was a zeta function. It converges very rapidly. So he just can calculate 1 plus 1 over 2 to the 4th. You only need to look at 3 or 4 terms and you estimate it, and it works very well. So he didn't even call it the zeta function. Now, since you've just flipped, interchange role of space and time, and this is Euclidean theory, these things must be equal. And turns out they are, due to this really remarkable relation. So this chi of z is the so-called completed zeta function. So you take zeta, multiply this combination of gamma function and pi to a certain power, and it has this beautiful symmetry that chi of z equals chi of 1 minus z. And Riemann proved that. It's not that easy to prove, but he managed to do it in that short paper. So basically, now nature apparently knows about analytic continuation, because if you do the calculation the other way, you do get this divergent quantity. But if you analytically continue zeta, then zeta minus 3 happens to be 1 over 120. And you can measure that. And the Casimir effect has been measured. And they measure this 1 over 120. The pole has some significance in physics also. So I'm going to be quick here. So if you look at BoseEinstein condensation, then if you look at the critical density times the thermal de Broglie wavelength at dth power, the critical point is defined by this equation. But notice that in 2 dimensions, you get zeta of 1, which is infinite. So Bose-Einstein condensation is not possible in 2 dimensions. And it's because of the pole. So in physics, this is a manifestation of this Honenberg-Coleman-Merman-Wagner theorem. In number theory, it just means that it's a consequence of there being an infinite number of primes. That's why it blows up. Okay. So let's get to the prime numbers. So this goes back to Gauss, where he asks a very simple question. Let's estimate how many primes there are less than x, some x. And when he was only 15 years old, and he guessed that it went as x over log x. And the way he did that, he had no analytic way of doing it. He just had a list of primes, and many of which he calculated himself, and just plotted various things and guessed this result. It was only proven 100 years later using Riemann's result. Okay? All you had to do was prove that the Riemann zeta function has no zeros with real part equals 1. And it turns out I'll explain that really quickly, but if you can prove that, you've proven the prime number, the so-called prime number theorem. Now Riemann did a lot more than that. This is just the leading term. What Riemann did is he found all the corrections. He expressed all the corrections of the leading term using Riemann zeros. So the key here, with the relationship between primes and the Riemann zeta function, is that there's something called the Euler product formula, which relates the zeta function to an infinite product over primes. Pn here is the nth prime. And that it's quite old, it's due to Euler, and it's pretty easy to derive. Take zeta, multiply it by 1 minus 1 over 2 to the z. It kills all the even integers here. Multiply by 1 minus 1 over 3 to the z. That kills everything that has a factor of 3. And you keep going. And then eventually you get 1 on the right-hand side. Okay. Now, something that's going to be important is that how do we know there's no zeros to the right of to the right with real part bigger than 1? And it's because that's the Euler product formula is valid there, and it's manifestly never 0. So in any region where the Euler product is valid, there can't be any zeros. So I'm going to try to extend the region of validity into the critical strip down to a half. Okay, and that's going to be the main strategy here. Let me quickly show you what Riemann's result looks like, in his paper. You don't have to understand all these things, but he basically had an explicit formula for the number of primes less than x. And it's an infinite sum. J here, this is the leading term I told you before, the log integral, it goes to x over log x. And then there's a same function here, but x to the row, where row are the zeros in the critical strip. This term comes from the trivial zeros, and it's a very explicit formula. And it's kind of fun to play with. Okay, so, so here, so pi of x is a step function. It jumps by 1 at each prime, 5, 7, etc. So it's kind of staircase function. If I just use 5 zeros in Riemann's formula, it's already looking reasonably good. Here's 20 zeros, okay, and here's 50 zeros. Okay, so you can reproduce this nice staircase function. So the zeros know about where the primes are. So in principle, if you calculate zeros, you can calculate primes. I'm going to tell you we've obtained something that is kind of the converse of that we can calculate zeros from the primes. So let's get to the primes. There's a lot of beautiful quotes on the primes. They're kind of mysterious. It's a basic question. How can the ordered set of integers lead to these seemingly random primes? And here's some nice quotes. One is, God may not play dice with the universe, but something strange is going on with the prime numbers. There's no apparent reason why one number is prime and another not. To the contrary, upon looking at these numbers, one has the feeling of being in the presence of one of the inexplicable secrets of creation. That's by Don Zagier, who's I met last summer. This one I like. It's evident that the primes are randomly distributed. It's evident. Unfortunately, we don't know what random means here. So I'm going to tell you a proposal for what random means here. Okay. There's a way of characterizing this. So we're going to use this pseudo-randomness. Now, for some technical reasons, I'm going to have to extend the zeta function to an infinite class of functions, as I told you, the so-called Dirichlet functions. So these aren't familiar to so many people, but there's something called a Dirichlet character, and it's mainly characterized by its modulus k. So I'm just going to tell you a few of its properties. It's periodic. It's multiplicative. So chi of nm is chi of n, that's chi of m. And they're all roots of unity. Okay, that's all we're going to use. Let me just give you 2 examples so you have something concrete in your mind, so you don't have to worry that you don't understand what these characters are. The simplest non-trivial one is mod 3. So, like I said, it's periodic. So it's 1, minus 1, 0. And then that repeats itself forever. 1, minus 1, 0. Very regular, kind of boring. Here's another example. This is mod 7. Okay, so again, it's just roots of unity. It's 6 roots of unity. And it has essentially all the same properties of the Riemann zeta function. So it has an Euler product formula. And it also has a functional equation that relates z to 1 minus z. And it's believed, it's called the generalized Riemann hypothesis, it's believed that this class of functions all satisfy the Riemann hypothesis. And it's an infinite class of functions because there's an infinite number of characters. Okay. So this is the first theorem that we proved. I'm going to change notation. I'll be referring to the complex variable as z. Standard number theoretic notation is sigma plus it. Right? So here's a simple statement. So let me consider this series. So take the characters, they're all roots of unity. So for any integer, the character is e to the I times some angle. And let me look at the series that is the sum of the cosine of these angles. It's really just the real part of the sum of the characters. So a simple statement is that if Cn is order square root of n, like rho is the square root of n, then the Riemann hypothesis is true. And the argument is the same as for the real part bigger than 1. Because if this series is true, if this growth is true, then the Euler product formula is valid to the right of 1/2. Okay? And as I said, wherever it's valid, then there's no, it can't be 0. So where this square root of n, almost every physicist who remembers his undergraduate education is going to think about random walks. Right? And this series, Cn, is the sum of, well, in the simplest cases, I mean, these were just 1s and minus 1s. And it's summed over the primes, so, well, let me just show you some examples. Well, here, this is to be more precise for the mathematicians, but let's just skip that. So let's look at this random walk property in more detail. Look, the angles are discrete, and they're equally spaced on the unit circle. Okay? Except for Riemann Zeta. So Riemann Zeta itself is going to be an exception. But let's look at the k equals 3 character. Right? So if you look at these characters over the integers, again, it's really very, very boring. But look at the characters over the primes. Well, there's one place at 0, which is at 3. But otherwise, it looks like, well, it looks like somewhat random sequence of 1s and minus 1s. Right? Now, there's a big caveat here, which is that this argument is not going to work for the Riemann Zeta function itself. Because there, all the chi's are 1. Right? So they don't average to 0. And there's no randomness there because they're all 1. So I'm going to have to, in mathematics, this is an important distinction that's been known for a long time. It's called the principal versus non-principal characters. So I'll be talking about the non-principal characters, which are all just roots of unity. We had current work in progress where we're trying to use some similar random properties for the Riemann Zeta function itself. But I'd rather not go into that. The work isn't published yet, and it would require me to talk about too much other stuff. Okay, but let's keep that in mind. Later on, I'll be plotting things for Riemann Zeta itself, just because it's more familiar to people here. But it's implicit that these things are valid for these non-principal Dirichlet characters. Okay. How do you prove this theorem? Not too hard. Basically, you take the Euler product, you expand it out. This is the leading term. I'm just looking at the real part. Oh, this doesn't work anymore? Okay. So I think maybe the battery ran out. Oh, no, there it is. It's going on and off. Okay, all right. So I take the real part. You have the sum over cosines over primes to the sigma. Look at this series. Now I'm going to look at C of x. So look at sum all the primes less than x times the cosine of these angles for the character. And there's a little trick, a well-known trick in mathematics where I can write this as an integral. And as long as C of x goes as square root of x, then that compensates here, gives you an extra square root of x here. So then this will actually converge for sigma bigger than 1/2 plus epsilon. If C of x, to be rigorous, you need this little epsilon there. Okay. But epsilon is something positive that's arbitrarily small. Okay, so here is where it gets kind of interesting. Again, look at this character mod 3 over the primes. So, well, if you look at it, it looks kind of random, but is it really random? Well, it's deterministic. Right? In principle, okay, you don't know all the primes. You probably can't calculate chi for the 10 to the 50th prime. We don't know how to do that. But you can certainly calculate the lower ones. It is deterministic. But look, there's an infinite number of primes. So essentially, once you get high enough, we don't know the primes, and we're not going to be able to calculate these 1s and minus 1s. Okay? So we're going to treat them statistically. So let's compare this with a Gedanken experiment. Okay, so take a coin, flip it every minute for 5 years, and write all the entries in a book. It's called the book. You can have your graduate student do this. Publish the book. Okay, so it was generated randomly, just a sequence of ones and minus ones. And once you've done 1,000, there's some anticipation of what's the next one going to be, right? But once it's flipped, it's flipped. And once it's written in the book, it's totally deterministic. Anyone in the world can look at the book, and then there's no more sense of anticipation. Everybody's going to agree on what the chi is for the 10 to the 10th. Well, not that many, but 10 to the, say, the millionth character. So this original random sequence it is deterministic now. And to quote a famous probabilist, here, if you think of this example, the distinction between randomness and determinism is kind of an illusion. His name was Billingsley, a famous probabilist. Now, there's a subject in both physics and mathematics called the single Brownian trajectory problem. Okay. So, usually when you think about random walks, we talk about an ensemble, right? You flip a coin, say 1,000 times, write the result, keep track of what they are, then start over again, do it another 1,000 times. And do this many, many times. So you have many, many states, and you generate an ensemble. And we know that if you histogram this ensemble, you're going to get a Gaussian. Right? So random walks leads to Gaussians. And Gaussians have this square root of n property. Right? So the question is, but suppose you can't repeat the experiment. Suppose you only have one graduate student. You don't have 100 to all do the same experiment and make a histogram. You only have one. Long series of ones and minus ones. What can you learn from that? Is it random? Is it not? Well, one way to do it, which has been explored in the math literature already, is to look at snapshots of it. So break out, you have a long, long series. Break it up into, say, the first million, then the second million, et cetera, et cetera. And you can go pretty high here, right? Even just with Mathematica. And then you generate an ensemble. So the ensemble is, so Cn, so little l here is the starting point. And I'm going to sum these cosines from little l to little l plus n, so there's n steps. But I'm going to take an ensemble of little l's, little starting points. Okay? So I tried to illustrate that here. So every green bar is the sequence, in a certain subset of the whole sequence. And since they go to infinity, I have a lot of room to play around here. Okay? Now, so if we believe that they're behaving like a random walk, you can apply a central limit theorem. Now, what is a central limit theorem? Requires two things. Well, you have to know the mean. So here, 1 and minus 1 is equally likely. So the mean is 0, and that's known. Dirichlet proved the theorem like that. The harder part is the independence. Okay? That one flip is independent of all the previous flips. You can probe that with these particular characters. Right? If you believe they're independent, then you can prove a central limit theorem. First, you have to calculate the variance. So b squared here, I don't want to, well, it's one or a half, I don't want to get into it. But the variance is the variance of these sequences, this expectation value of these, we call them block variables. And there's an interesting correction, which was due to a mathematician here at Stanford, Sandharajan. It's kind of hard to pronounce his name. I met him yesterday, and he just says, "Call me Sound." Very interesting and pleasant person. And this is a younger person that worked with him. So this is an interesting. I would think of this as a finite size correction, right? Because when little l is getting very, very large, this prime is very, very large, and log over log is going to 0. So these terms vanish in the limit where l is getting very, very large. And then, so this is going to 1, and then the variance goes as n, okay? Which is looks actually like a random walk. So if you have this independence, we've normalized it properly, then the central limit theorem would be that this ensemble, histogrammed it, normalized by 1 over sigma n, which is square root of n, would approach in distribution, that's what this symbol means here, in distribution it would approach the normal distribution. The standard one, with variance 1 and mean 0. And to most physicists, this would mean that Cn grows as square root of n. But it turns out that's not completely rigorous mathematically. Okay? But you can say things a bit more precise, but I don't want to get into it right now. So we tested that. So if this sequence if there was some secret correlation, between the values of the characters over the primes, the central limit theorem would fail because it assumes independence. Okay? So we checked this. So here I generated, it turns out to be 10,000 states. The block variables, the n here, the number of steps was 6,000. And each of these 6,000, they were separated by a distance of 100 primes. Okay? And you get a perfect normal distribution. And if you fit, fit gives you a 0.004 and 1.01, and the so-called p-value is essentially 1. So it's almost essentially a perfect fit. So this is a very good indication that these characters are behaving like a random walk. Okay. I like this quote too. There must be something mysterious about the normal law, since mathematicians think it is a law of nature, whereas physicists are convinced that it is a mathematical theorem. So what he's referring to is the mathematicians are thinking, this is like, you have a data set, comes from, if you're a psychiatrist, psychologist, or sociologist, you have some data set and you apply the normal law, and it's all a part of nature. But it is a theorem. The central limit theorem is a theorem. You prove these things. Yeah? Mm-hmm.
You said that the p-value was very close to 1.
Very close to 1, yeah.
It's unusual for random distribution.
I know, it's almost better than a random walk.
It is better.
Yeah, we're a little surprised that it's almost, we compared like a real random walk to this series, and the p-values for the sum of our primes was higher. It almost, to be close to 1 is almost impossible. But it was like 0.99, it was pretty amazing. So there's no theorem here yet, but we believe that this to be true. And it would be enough for the Riemann hypothesis. Here's a little bit of numerical evidence. So what I'm saying here is that the Euler product converges to the right of 1/2. That means you can calculate the zeta function in that region using the primes. Let's see how well that works. Here, again, the caveat is this should be for this principal character, and not the principal character. Okay, but I'm going to plot it for zeta itself, because it turns out that if you truncate the product, you still get a very good approximation. Okay, so here I'm looking at zeta of 3/4. The real part is 3/4. That's inside the critical strip. It's not supposed to converge. So the solid line is the actual zeta function, and then I calculate it with the Euler product, keeping, say, only 5 primes. And it's already looking pretty good. Okay. Once you get beyond 1,000, you can't really tell the difference here. Okay, so it really seems to be converging. You definitely see a transition at 1/2. Okay, if I try to do the same thing for here, zeta is to the left. All right, I took sigma. The real part was 0.04. So now I'm a bit to the left of the critical line. This whole thing just falls apart. Okay, and you can see it here too. Okay, here's the actual value of zeta versus the truncated Euler product, and at 1/2, you see they just completely don't agree. Okay. Okay, so I'm going to leave this random walk business and I'll come back to it toward the end. This thing only works sporadically, but I think it'll be all right. So this, changing gears, I derived some transcendental equations satisfied by the individual zeros. And surprisingly, it was not in the literature. Everyone, suppose you said, well, everyone here knows a function where all the zeros are on a line, right? Cosine, right? We all know that, but here z is a complex variable. But if you think about it, there's still something to prove. Okay, so it definitely was proven a long time ago. So cosine of z is 0 whenever z is an integer, half-integer multiple of pi, right? I'm going to put, so when you're trying to find zeros, you're trying to find the roots to this equation, which is really two equations, the real and imaginary part. So it's just all the infinite number of zeros all come from one equation. I'm going to replace that with an infinite number of equations, one for every individual zero, by putting the zeros into one-to-one correspondence with the zeros of the cosine. Okay? So the equation is only going to depend on n, where n is, say, the nth zero. So you tell me I want to know the 1,000th zero, I'm going to show you an equation, you just plug in n is 1,000, and you get the zero, the ordinate of the zero. So let me describe this equation. Remember my function chi, the completed zeta function. Let's write it. It has an argument. Let's call it phi, and then some modulus. Mm-hmm. So we argued, I think proved, that at each zero, the cosine of this angle phi here is 0. Okay. So phi has to be n minus 3/2 pi. This is a convention that the first zero is n equals 1. Now, the nth zero on the line is of this form. And this is the equation that it satisfies. Okay. So it involves the log of the gamma function, imaginary part. There's the linear term. Unfortunately, there's still some reference to the zeta function because this term is the argument of zeta. This term is very small, turns out, compared to this. So suppose I want to calculate a very, very high zero, 10 to the 100. Okay. Well, we have the Stirling approximation. So the log gamma part is easy. I can use Stirling formula, and then mathematically I can set the precision to be 100 digits, and it can calculate that part. Okay. However, it can't calculate the arg of zeta, because if you try to calculate the zeta function in Mathematica, it can only go so high up. I forget what, but you try to type in zeta of 1/2 plus 10 to the 10. I think it starts to fail. It won't give anything. Right? So, but the arg of zeta, if the Euler product formula is valid, I can express the argument of zeta just by taking the log of the Euler product. Okay? So I'm going to calculate, so the notation here is t little n, the little n is the nth zero, the big N is the number of primes I'm using to calculate, to calculate the argument of zeta. Then I could just use a root finder software in Mathematica to solve this equation. This part is easy. I keep a finite number of primes, and then Stirling formula gives this stuff. So it's kind of interesting because this is an equation for every individual zero. And but the equation itself refers to all the primes. So in a sense, every single zero of the zeta knows about all the primes, so it has to satisfy this equation. There's another theorem here which originally I thought was going to be very promising, but it didn't quite work out. But it is a theorem that, if there's a unique solution to this equation I just showed you for every n, then the Riemann hypothesis is true. And the reason is there's Riemann knew part of the answer to this, but a mathematician in the early 1900s named Backlund, using something called the argument principle, came up with a formula for the number of zeros up to a certain height, called it big T, okay? So if you want to count the number of zeros up to a certain height, there's an exact known formula for that, right? And, but it doesn't tell you if the zeros are all on the line. It's counting all zeros. If there's a zero off the line, well, it's going to be counted in multiplicity 2. Okay, so it can't tell. But I gave you a formula that calculates the zeros on the line. And they're already enumerated by an integer n. So I can count them. Right? And then it turns out that, so let that be n0 of t. Using our formula, we calculate the number of zeros up to a certain height on the line. And it turns out that it equals the known function for the number of zeros in the whole strip. So it must mean that all the zeros are on the line. The problem was that the part of the equation that is arg of zeta is hard to control. Okay, and it fluctuates like crazy, and for that reason we couldn't control it enough to prove there's a unique solution for every n. Okay, but we believe it's true. We went to pretty high n. Suppose, well, here's another reason to believe it's true. If I ignore that fluctuating term, the arg zeta, then the equation is quite simple, right? It just looks like t log t equals an integer. That turns out to be exactly solvable and have a unique solution in terms of something called the Lambert W function, which has recently been popularized by the people responsible for Maple in Canada. So they put out this poster. So the Lambert function is W is a solution to this equation. W times e to the W is z. Okay, and they're promoting it as a very fundamental function, as fundamental as the logarithm itself. So Lambert was kind of interesting. I mean, he's the one that invented the notation cosh for hyperbolic cosine and tangent, etc. He was the first to prove that pi was irrational. You would think that that Euler would have known that, but apparently not. So this approximation works extremely well. So it's a very smooth curve. So here I'm plotting. So the straight line, that's a straight line, but the solid curve is the Lambert approximation. And the dots are, well, this is the 5th zero, this is the 10th zero. Okay? And they're quite regular. I mean, it really captures the main, doesn't capture everything, it's not exact. There's small fluctuations around the Lambert approximation, but it's actually pretty good. Okay? So, test my some of these ideas, I decided to try to calculate some very high zeros. Some of them are known, so I can do some test cases. So Lisco is famous for this. So he calculates some zeros around the 10 to the 21st and some zeros around the 10 to the 22nd. And actually one of his students is now calculating zeros around the 10 to the 30 or something like that. Okay? So the answer is known. Okay? Now, in this case, there's a jump here because there's essentially 10 to the 22 zeros between here and here. Okay. But these are the results you can get from their tables. Okay. Now I'm going to try to calculate this with 1,000,000 primes. Okay. Reasonable. So mathematically can do this. Of course, it knows the first 1,000,000 primes. It knows a lot more primes, but that equation turns out find root actually works pretty well, and it spits out a number. And this Lambert approximation always gets the first n digits right. Because this is 10 to the 21st. The first 21 digits are correctly predicted by this Lambert approximation. Then this arg zeta term that I'm neglecting, that's neglected in this Lambert approximation, gives some small corrections, which are the digits beyond the point. Okay, so let's go, and they're quite good. I mean, some of them are better than others, but so I'm getting things like 0.505. The correct result is 0.498. So it's pretty close. All these digits match here. And I think it's because I've only used 1 million primes. If I was able to use a lot more primes, I would just improve this. Okay? These small errors. So now I'm ready to calculate the 10 to the 100th. Because I've checked the method. It seems to work. It turns out, for reasons I'm not telling you, the higher the n, the higher up you are in the order, the better this approximation is, it turns out. So for the Google 0, I'm very confident the first 100 digits are right. And I've studied a bit how it scales. I'm very confident that the next 3 digits, the 0.244, are correct. Okay. Now it's going to take a long time to check this, unfortunately, because you have to implement the zeta function to that height, and that's a very, very challenging problem. But I hope someday it will be checked. Okay, good. So I didn't go over time. So conclusions. So this is a well-known belief that the Riemann hypothesis needs 2 things. The Euler product formula. So all the functions that are believed to satisfy Riemann hypothesis have an Euler product and a functional equation. Okay. So obviously I need the functional equation because using the Euler product, I'm trying to get down to 1/2. So I can control all the zeros to the right of 1/2. But then the functional equation relates something beyond 1/2 to something on the other side. So I only need convergence to the right of the critical line, and then the symmetry implies there's no zeros to the left of the critical line. So you're done. You're done. So I presented 2 things. This kind of random walk property, which I say is behind the convergence of the Euler product formula to the right of 1/2. And I presented some transcendental equations, which are completely independent, but you can put them two together and then calculate the very high zeros. There's some counterexamples to the Riemann hypothesis where these are quite old works, but there's some functions that were cooked up. They're actually linear combinations of the Dirichlet L functions, which satisfy the functional equation, but because they're a linear combination of L functions, they don't satisfy an Euler product. And those functions indeed have zeros off the line. Okay? So it's believed that this Euler product is necessary for the Riemann hypothesis to be true. So in those examples of these equations that don't have no Euler product formula, we find that there's no solution to the transcendental equation you propose. And that's because there's zeros off the line. Finally, this whole reasoning in terms of random walks applies to another infinite class of L functions that are based on modular forms. In particular, the simplest one is the bosonic string partition function, the inverse of it. You take that partition function, look at this Fourier expansion that defines some coefficients. They're called Ramanujan tau. And then you define your L function using those coefficients. And then the same argument gets the extra square root, gets you down to the Riemann hypothesis, the analog of the critical line. And that uses some reasonably recent results, well, 1975, their result of Deligne. So at least there's a unified perspective on these very different infinite classes of L functions. So I think it's at least it's a unified approach. And it really boils down to this, with this random walk property and this Gaussian distribution, which we have not proven. Okay, I mean, I really just gave a lot of numerical evidence for it, but I certainly did not, prove a theorem there. Okay. Okay, thank you for your attention.
Try this one. So there is an approach taken by George Sordas, who was his family emeritus at University of Hawaii, and that has to do with positivity of certain determinants of certain matrices. So I would say that's a particularly promising approach as I've looked at it. The difficulty in its execution for a proof is that there's a statement in one of Sordas's papers, Sordas, Norfolk, and Varga.
How old is this
Well,
work?
it's either I was trying to remember, it's either 89, 93. But on the scale of things, that's recent.
Yeah, right.
But Varga was doing the numerics, and it turns out, at least it's my view, that there's an error in one of the key statements, that the key function that they have they say it always turns around eventually. But if done in Maple, which is my preferred code, it doesn't turn around. And so it's as though there's this path to a proof of the Riemann hypothesis, but there's a big sign that says trail closed by this paper of Sordas, Norfolk, and Varga. But in fact, the trail's open. And I think that's a particularly promising avenue. And it doesn't rely on analysis. It really has just to do with positivity of certain determinants. And if you give me another moment, since you seem interested. So Nima Arkani-Hamed talks, and he gives many talks.
Yeah.
And he points out there's this connection between cluster algebras in mathematics, which bring about associahedra, his amplitude hedra, and the Riemann hypothesis, and then I have some other things. And they're all connected by the positivity of certain determinants. And so I think what will replace the Riemann hypothesis in the future is positivity, and that is the most fundamental mathematical structure that hasn't been cracked yet.
I'm not familiar with that work,
Okay.
but I'd be. Where does the information about Riemann Zeta come in? Is there a connection with primes in that approach? Maybe we can talk about it after.
Since you asked me, and I don't mean to take the time, but the notion that's always given in talks like yours, without negative criticism, is that the Riemann hypothesis is about prime numbers. And of course it is, because the zeta function through Euler is related to the part of the Riemann hypothesis that's not proved, that Polya here at Stanford could not prove, is not, the part that's not proved is not, in my view, about prime numbers. It's about positivity of certain determinants. And Arkani-Hamed's amplitude-hedron and the cancellations that happen that are miraculous also is related to positivity of determinants. And so the connection with prime numbers is basically, that was done by Polya. All of that is done. What remains is to show the positivity of certain determinants.
Well, I'll have to look at that. You can probably find my email and then maybe send me a reference, or even just send me the name and I can find it myself. Maybe it sounds interesting. I've heard lots of talks by Nima Arkani-Hamed. He comes to Cornell. He's a professor at large at Cornell, I've heard many talks about this amplitude hedron. But yeah, I've never seen him talk about the Riemann hypothesis, though. But
He makes the connection.
maybe it's
They're
more
all
recent.
interconnected. There may be 6 different things that are connected.
I have a question. You look at the principal character, you don't get a random walk, as far as I can tell.
Right, right.
It would be impossible to believe that the theorem is hypothesis is true in both cases, but for completely different reasons. So there must be a random walk.
No, that's a very good point. You know, but we're working on. There's two approaches to try to get back to Zeta itself. It turns out that if you look at a truncated Euler product, so you truncate n, it's a very, very good approximation. So I did some work on that, but Gonik is more famous for that. He's a number theorist. There's another approach I'm following lately with my collaborator, Mosardo. If you look at the inverse, so what's killing you for the principal case is the pole. You know, regions of convergence of analytic functions are always half planes. So if you have a pole there, you know it can only converge to the right of 1 because there's a pole at 1. The non-principal case, there's no pole. That's why this is even possible. But if you look at the inverse of the L function, you can do some work there using this Mobius mu function. And that would be an approach that still relies on the sort of multiplicative independence of the primes. But it wouldn't be the same argument, though. Yeah, no, it's a little disconcerting. Yeah, I agree. Yeah.
Last year, Michael Atiyah asserted that there was a connection between the fine structure concept and the Riemann hypothesis. Can you see any way that they can be related? I mean, the derivation of fine structure?
No, I'm afraid not. Pretty confident about that one.
Any other questions?
Well, I can add, in Atiyah's talk, which was at the Heidelberg conference for young people interested in science, he was getting very elderly and he was having trouble with his logic. Well, one thing he mentioned was that in the Riemann hypothesis proof, which he was claiming at that conference,
Right.
Unfortunately, and it's been removed from the web, and
Right.
all in due course, I think. But one thing he did mention was that the Riemann hypothesis proof that he had would rely on super exponentiation types of functions. And I think those super exponentials he tied in with the fine structure constant. And in my own work, I'm using, just quite apart from Atiyah's talk, I'm using super exponential functions, or a Riemann proof. So that's just to fill in the gap there.
No, I looked at Atiyah's paper. I don't even know what properties the zeta function used. I don't see where the Riemann zeta function actually came in. You got to, at some point, you got to use some properties of the Riemann zeta function if you're trying to prove the Riemann hypothesis. I couldn't see anything about them. Anyway,
remember his statements were made in late age, and
right, you know,
should be forgiven that.
No, I think everybody in the math community, that's why there wasn't a lot of criticism. It's exactly because of that. Yeah.
Can I ask you a question?
Hi, Steve.
A little bit more down to earth. Do you see in your approach why the zeros of the L functions are distributed like a random matrix?
No, I don't see that. And that's something independent, and I can't address that. I don't see that. Well, I really just don't know how to relate those two things. Yeah, because there is some randomness in the zeros themselves. It's still a conjecture, though, that they're described by random matrix theory. But it's very likely to be true. But I don't know how to connect that to the randomness I'm talking about. But the randomness I'm talking about is pretty robust because it's a random walk, right? It's just a square root of n you're trying to get. So it doesn't have a lot of details. I think it's more robust than the random matrix business. Yeah. But I would like to relate them, but I don't know how to do it.
Thank you.
All right, thank you.
Mathematicians in the audience, do you know?
I see. I don't.